Okay, so this lecture is going to cover Chapter 5, Part 3, and specifically we're going to be talking about standardization and linear transformations. So I want to start the discussion on this concept of standardization by referring back to the footprint that I found when I was a young man on the Mad River, fishing on the Mad River, 14¼ inches. And of course, this is referring to what I like to call the Bigfoot hypothesis. Just to remind you of this hypothesis, the null is that Bigfoot does not exist, which of course makes sense because as the null hypothesis, because this is the prevailing point of view or the status quo. And then the theory that we might have, or that even some researchers have, is that Bigfoot does exist. And this is a natural statistical hypothesis because it's a dichotomy. One of these two things is true. The null or the alternate is true. And if one is true, they're mutually exclusive. It means the other one can't be true, or they can't be true at the same time. So and typically what we do in statistics is we assume the null is true until we gather data or evidence that contradicts the null to the point that we can no longer believe it. And so the statistical approach to the question would be, just how big is a 14¼ inch foot for a human male? Now, remember that in order to describe the population, and let's talk about that population just for a minute. I want to write down the population that we're studying here. Lengths of male human feet. Okay, and we could get real specific here. U.S. males. Are we talking global? I'm not going to get caught up in the minutiae here, but most likely it was a U.S. male. Of course, it could have been somebody from another country visiting that left the footprint. I don't really know. But again, this is mostly meant as an academic kind of an exercise and kind of a fun example that we can use to talk about the statistical ideas. So what I did is a little research, and I found out that according to the American Academy of Orthopedic Surgeons, the average male shoe size is 10½. But I need that converted to inches. Now, average, they're not being clear here. I don't know if they mean average in terms of the median, or I don't know if they mean average in terms of the mode, or average in terms of the mean. But I'm just going to assume that they're talking about mu here, okay? And remember, when we're describing a population numerically, I need two measures. I need the mean and I need the standard deviation. First of all, I'm going to talk about the mean here. And then the other issue I have, or that we have to rectify or deal with, is this idea that really shoe sizes are not uniform. They actually span intervals, really. And if you've ever been shoe shopping, then I'm sure you realize that some brands run small, some run large. And so when I'm looking at this, and of course look at the top scale because that's the foot size corresponding to the shoe size. And what we can see is that according to this chart, 10½-inch shoes, or I'm sorry, size 10½ shoes look like they roughly span 11 to 11¼ inches. So if we split the difference here and take this, the value halfway between, then we might reasonably conclude that the average length of a male human, of course these are U.S. males because the chart I'm looking at is for U.S. males here, but that I'm going to assume, okay, and then statistics, this is pretty much how we have to do statistics. We make assumptions. I'm going to assume that the average length of a male human foot is about 11⅛ inches. But that still leaves me with this question of what's the standard deviation? And I searched around on the internet and I didn't find this number. Now that number may be out there. I didn't spend hours and hours looking for it, but I haven't had much success here. But I do have a trick up my sleeve, and it turns out there's quite a bit of information out there on large feet. And I ran across, I couldn't help but copy this photo. This guy's got a big foot. Carl Griffiths, he's actually from Great Britain, but his foot's is almost 15 inches. And I also found a number of other people out there with feet in that were close to this same size. But the conclusion that I came to is that 15 inches is getting out there. That's about as big as male human feet get. 15 inches is a large foot. Now, let's talk about modeling the population. Okay, because what we do in statistics, what we have to do, and one of the places that mathematics comes to play is in modeling the population. And what do I mean by this? Well, when I'm talking about, in this context, when I'm talking about modeling the population, I'm talking about, I'm really addressing this question. What's the distribution? What is the distribution here? Okay, so let me show you the steps. So the first thing I need if I'm going to use mathematics to model a population, I need a variable. And of course, those of you, you all had algebra, so you know how important variables are in math. So I'm going to define a variable x, and I'm going to say x is the length of a randomly selected, so there's that word random coming up, randomly selected male human. And remember, I'm assuming human because the null is true. Bigfoot does not exist. Bigfoot does not exist. The foot is a human foot. The footprint I found came from a human foot. And so now that I have a variable, the next natural thing to do is to draw an axis. So that's the next thing I'm going to do. So I'm going to draw an axis, and I'm going to label it with x. Now again, thinking back to algebra, this x-axis is representing in statistics, we'd call this the sample space. But in algebra, really what we're talking about here is the domain. So in algebra, we call it the domain, and in statistics, we'll refer to it as the sample space, meaning here is this axis represents the set of all possible x values that we could be talking about here. Now, I need to think about what the distribution looks like. And I'm going to make another assumption here. I'm going to say, okay, I'm going to assume that the population of male human foot sizes follows a bell curve, okay? And this is my model now, and they'll be down the road in chapter 6 actually, we'll be talking about the normal distribution, and there's actually a function that draws this curve, but I'm not worried about that right now, okay? I'm just working on this idea of how big is this footprint really? And what I'm putting right in the middle is our population mean that that I came up with of 11 1/8 inches. Now the idea here is that the idea with the curve is that this range where the mound is, this is the range of the typical, okay, or and as we go out in this direction, these are more and more unusual. This is the idea with the bell curve. So the reason the tail comes down like this is because it's telling us that there's a rapid decrease in the proportion of the population with foot sizes as you go to the right here. And so I might put 15 way down the way here and say that tail of the normal distribution, or the bell curve, is going to be getting really close to the axis there at 15. Now, because of the symmetry of the model I've chose to use, and based on the assumption I'm making, there would also be the same kind of unusual pattern as we go to the left. And so the other natural question would be, well, what's the lower, what's a really like super small male human foot? Well, if we think about this distance from 11 and a quarter or 11 and an eighth up to 15, that means this distance is about, what is that? That should be about 3 and 7/8. So this is about 3.875 units. And so we could argue that it makes sense to say, because of the symmetry, that the unusually small-footed males would be down here at 11 and an eighth minus 3 and 7/8. And that puts us down here at about 7 and a quarter inches. So then we can check our assumptions a little bit mentally and think about, okay, based on our experiences, of course, I've seen thousands of barefoot men in my life and footprints on the beach. And if I think about my experience, I'd say, yeah, that's a pretty small foot, 11 and a quarter or 7 and a quarter inches. I haven't seen too many guys, too many adult males, and that's the other thing I didn't put in here. There's always something, right? We're talking about adults here, okay? That's not maybe entirely obvious, but again, it doesn't even make sense to talk about women or children, because the foot I found, the track was so large that the chance that it was a woman is even smaller, and the chance that it was a child was even smaller yet. So nonetheless, I don't know if that's obvious or not. But in any case, here is the situation, okay? What we're going to say, one of the things that you're going to learn, and I'll bring it up now, is that if you have a population that's following a normal distribution, then about 99.7%, virtually the entire population, will be within 3 standard deviations of the mean, okay? And so this concept of thinking about the most extreme on both ends, and I'm going to focus on the 15 because really what I'm saying here is that to get to 15, I would go, if I'm making the assumption that I'm spanning virtually all the population in 3 standard deviations, then if I take this number, this distance from the mean to that really large number, 15, then I could estimate sigma by saying sigma is about 3.875 divided by 3 standard deviations. Now, the idea here is that, again, I searched around on the internet. I found the biggest foot I could find for a man, and this 19-year-old Griffiths guy had a 15-inch foot. There are a few others out there. There might be some even a little bigger. I don't know. But nonetheless, 15 seems like the absolute upper bound for male foot lengths. So if I use this concept of the normal distribution, that's my model, and I say that then again, this percentage comes from, so I'll just make a note. It'll come up again. But this percentage is based on something we call the empirical rule and it's a property of the normal distribution or normally distributed populations. Then I can make the argument that the standard deviation is about that distance from the mean to, oops. Let's see, 875. So that gives me a standard deviation of about 1.3 inches, okay? And so based on these assumptions and this analysis, then I'm going to model the population as follows. Here's my model, Okay. The population is normally distributed. Here's some notation. It's foreshadowing some ideas to come. But when I put an N with a parenthesis, first number is the mean, second number is the standard deviation. So the model that I'm going to use is that the variable x is normally distributed with the mean of 11 and an eighth and a standard deviation of 1.3. Okay, so now I have the population described. Let's talk about that. Whoops, I'm sorry. Let's talk about that actual measurement that I found. So the x value I found was 14.25 inches. The population, the model for the population that I'm using says, and this is based on assumptions, of course, but I'm saying that the mean is about 11.25 inches and the standard deviation is about 1.3 inches. Okay, so now one way to think about it again is I could look at that axis and say, yeah, 14.5. When I lost my normal curve here. Let me sketch it up here again real quick. So when I'm thinking about this normal curve here and how the population's distributed, one way to think about it is, well, so here's my x variable, and 15 was down here somewhere. And that 14.25 is down here, really getting pretty close to the 15. And later on, what we'll actually do is we'll do some calculations, and we'll actually look at the proportion of the population with feet at least this big, okay? But that's down the road, and we're not there yet. This idea here with area, that's a Chapter 6 idea, and we'll get to it. But what we're talking about right now is this concept of standardization. And so what does that mean? Well, let's look at a calculation here. If I take x, my x value, that's the data value that I found, 14.25, and I subtract the mean of 11.125, and then I divide that by 1.3, I get a number, all right? And the number I get is approximately 2.4. Now, I want you to, so what does this number mean? Or what does this number represent? Well, let's talk about units here for a minute, okay? So when I take this difference in the numerator, and some of you might be familiar with unit analysis, but when I take this difference in the numerator, the difference is in inches. And 1.3 as a standard deviation is in inches as well. So those units cancel. And the question becomes, what are the units on 2.4? Well, there are actually a couple of different ways to look at it. Since inches cancel, then we might say that that quantity doesn't have units. But what I like to think about this number, the way I like to think about this is that the units are SDs. And what does SD stand for? Standard deviations. So think about it for a minute here. So when I take the difference in the numerator here, and what does that give me? The difference here is, what is that? About 3 1/8 inches. That's about 3.125. So the distance from 14.25 to the mean is about 3 1/8 inches, okay? And when I divide it by 1.3, and remember, 1.3 is the standard deviation, what I end up with is about 2.4 standard deviations. So this transformation now that I'm beginning to talk about is always going to give us a number that has the same interpretation, and that's why we call it a standardization. when I do this calculation, taking my data value, subtracting a mean, and dividing that difference by a standard deviation, the number I get is always in standard deviation units. So that footprint length, 14.25, was about 2.4 standard deviations from the mean. Now, Ronald Fisher gave us some conventions, or some ideas that turned into conventions. And basically, any I'm going to call it an x value. Any x value, all right, and this is going to get more more detailed later on, but let's just keep it simple right now. We'll talk about any x value that's more than 2 standard deviations from mu is rare and unusual. And this is actually also based on the empirical rule, but I'll talk about that more later on when we get to it. But for now, I just want to point out that one of the useful things about doing this conversion is I take a number like 14¼ inches, and I think, man, that's a Bigfoot. But the question is, how big is it? Well, I can't really answer that question until I know a little more about the population. Specifically, what's a typical foot length? And then how much do humans tend to vary? Human male foot lengths tend to vary on average from that typical. That's the standard deviation. So that's the information the mean and the standard deviation give me. And then when I do this conversion or this transformation, I get a number that tells me how many standard deviations that measurement was, or that data value was, from the mean. And then I can apply Fisher's convention of 2 standard deviations or more being rare and unusual, and say, okay, Fisher would say that foot track length was rare and unusual. Okay. And again, recall that we start to question the null based on information, data in this case, that is rare and unusual. Now I want to talk a little bit about this standardization transformation, okay? And it's something we call a linear transformation. So I'm going to take a minute and talk about that. Now I was using mu and sigma, and it turns out there's really 2 different versions of this formula. In the beginning of the textbook, you know, and this, since the standardization transformation comes up in Chapter 5, this is right before Chapter 6, which is where the normal distributions discuss. So there's actually another way to look at this, but for now, let's just talk about this. And again, we're not talking in Chapter 5. We're talking about data, not populations, and that's why in Chapter 5, the transformation has the sample mean and the sample standard deviation. All right, so I want to look at this in 2 different ways. We got the data, and then we got the population. And more in this class, we're going to move towards inferential statistics, which deals with the population. But in Chapter 5, the transformation takes this form. Okay, and I'm not going to bother with the x. I'm just going to call it s. Whoops. Oops, see, and I love it when I do that. Oh, I screwed up. All right, let me rewrite that. So data, and then we have population. There's a little button on this stylus pen I'm using, and then when I accidentally touch it, it advances the slide. But in any case, when we're dealing with data, we don't have the mean and the population mean mu and sigma, the population standard deviation. We'll use this transformation. But when we have population parameters, like in the previous case, I can use mu and sigma. Notice the form of the transformation's the same in either case. Now, this is what we call a linear transformation because, and we can do some algebra to show this, and that's what this little box, this white box, came right out of the textbook. And since we can do some algebra here, okay, I'm going to put a couple of extra steps. I'm going to put an extra step in here. So S is in the denominator, so I can split that denominator into two parts. And then the last step the textbook did, or the textbook just wrote this down. This can be written as 1 over S times X minus X bar over S. And so what they're saying here is that if we let A be 1 over S and we let B be X bar over S, then what we end up with is this is a linear form or a linear expression. The same argument can be made for the population parameters as well. So this would be 1 over sigma instead of S, and then this would be minus mu over sigma. And since mu and sigma are both constants, then both of these transformations are linear transformations. Now there's a couple of properties here. We say the variable is standardized if it has a mean of 0 and a standard deviation of 1. The transformation we're talking about here will always take X and transform it to a new variable that has those properties. And it's hard to understand this right at this point, I know, but when we get to the population discussion in Chapter 6, we'll actually put a variable here called Z. And as it turns out, Z and X, now this is looking a lot like a linear form. Of course, a linear equation. Of course, the ones you're most familiar with from algebra are like the slope-intercept form, y equal mx plus b. And the argument I'm making here is that what we have is z equal ax minus b, which is of the same form. And again, this is just the first introduction to this idea. We'll talk about it some more down the road. Now, linear transformations have some special properties, and we'll talk about those in a minute. But right now, what I want to do is an example right out of the textbook. So the first thing, so what we have here are some scores, a particular student's scores over here on the far right, and for a particular exam, and it's probably like a standardized exam. We'll talk, and that's sort of the point. What does it mean to look at somebody's standard score? But we're asked to do some calculations. We're asked to convert each score to its corresponding standard score. And notice the book, this problem is talking about population means and population standard deviations. So this is, so the transformation that I'm going to be using, this is sort of, again, foreshadowing a little bit, but the transformation is going to be X minus mu over sigma, which specifically is X minus, well, in each case it'll be different. For the stats one, for example, it's going to be X minus 67.2 divided by the standard deviation, which is 10.3, okay? And then, of course, for the logic part and the verbal part, the transformation will be a little bit different. But let's take a look here. Let me write this out. So we got stats, or is this the stats part of the exam. So the calculation would be the score, this is like the X value, minus the mean, 67.2, divided by the standard deviation, 10.3. And when you do the calculation, you get negative 0.41. And then we'll do the same calculation for logic. So let's see, the student score was a 61, average or the mean score was a 56.3, divide that by 6.7. And what we get is about, and again, this should be approximately 2. I rounded this off, but that's approximately equal to negative 0.41. This one's approximately equal to 0.70. And then the last part we have here of the last calculation or transformation is for the verbal part. And let's see, so we'd have 57 minus 50.9 divided by 3.2, and that's about 1.9. So so when you look at the scores individually, untransformed, you might say, well, the verbal score is the lowest score. But that's not taking into account what the typical score was for the exam, the mean score, and that's also not taking into account how much the scores varied from the typical. So what the transformation does, what the standardization transformation does, is it gives us numbers that are more comparable to each other, and comparable in a different way. So the next thing I want to talk about on the same problem, okay, is the concept of scaling, okay? And let me do it this way. So I want to look at 3 different axes, okay? Because again, we have a variable. I'm going to define a variable, okay? We'll use x again. And I'm going to be a little bit vague here, okay, because we got 3 different exams, but I'm going to use the same variable for each exam, x. And so let's see, there were 3 different exams. One was the quantitative, or we'll just call it stats. And so the axis that I want to look at here, okay, again, I'm thinking bell curve, but I don't want to draw a bell curve. I'm drawing a scale though, because really one of the ways to think about these transformations is in terms of scaling. So 67.2, that was the mean, okay, for the stats exam. This is the x-axis. And let's see. So I'm going to use standard deviation units here. So let's see if let's go with 2 standard deviations on either side. So the standard deviation for the stats score was 10.3. So if I add 10.3, I get about 77.5 here. That's a 7. And then another 10.5 gives about, or 10.3 I mean, gives about 87.8. And then 56.9 here. And 46.6 here. And the student's score in question was a 63. And so a 63 maybe is right, like maybe right there. Then we got the logic exam. So let's look at the logic exam here. And do the same kind of thing, draw an axis, put a variable x, and then the average for the logic exam was 56.3, so I'll put 56.3 right in the middle, and the standard deviation was 6.7, so if I scale my axis again using the standard deviation units here, let's see, I think that's about 63 and 69.7 and 49.6 and 42.9. And on this scaling system, 61 is maybe right about there. And then the verbal test would look something like this. And the average for the verbal test was 50.9. So I'll put that right in the middle, and I'll do the same kind of thing as before. So this is about 54.1 here. And then what I'm doing here is just adding the standard deviation of 3.2. And so one of the points that I'm making here, or trying to make, is that each particular exam score in its raw form has to be looked at using a different scaling system. And if I drew all three of these axes out, and again, let me put 57. Where would 57 would be? Right about here. So again, if I drew this out with these three different coordinate systems, okay, this is like each one of these coordinate systems I'm creating is centered on a different mu, because we've got the mean for the stats, the mean for the logic, the mean for the verbal, right? Those are all different averages, and then of course they all have different standard deviations as well. But looking at this spatially, I can see that this score for the verbal is the highest score out of the three, relatively speaking. But the really cool thing that happens here, and the reason I wanted to show you the scaling, and this is something that I've really begun to understand the more I teach statistics, is the importance for students to look at scaling of axes and to think about what is happening with the axes. Well, first of all, when I use a transformation, x minus mu over sigma, and this is kind of the generic form, right? Each one of the three different exams had a different mean and standard deviation. But the idea here is that when I put all of those through this same transformation, okay, with different numbers, right, of course, depending on what the mean and the standard deviation is, all three of those means go to the same place on the new axis I'm creating, which is 0. Okay, and if I go and use the formula I was talking about earlier, where I set this transformed variable x to another variable, then I could actually put a label on this new axis and call it the z-axis. And then the way I would scale the z-axis relative to the three axes above are using 0, 1, 2, and 3. Because the transformed variables are going to have a mean that is 0 and a standard deviation that's 1, and that comes from the previous definition, the definition of a linear transformation. And so now notice that the three different x's I put on the three different axes, okay, now can all go on the same axis, okay? Negative 0.41 is right about here, negative 0.7 is right about there, and negative 1.9 is right about there. So this is another kind of visual way to see how this standardization transformation puts all of these different distribution. Again, I'm already using the word distribution because I don't know what the distribution is for scores on these exams. That would take research and investigation. But I know that, but what I could say is if I did give it a model, say I called it normal, I don't know if it is or not, but just say that we're going to do a lot with the normal distribution. Each of these three different exams would have different normal distributions. And the key thing here, one of the key ideas is to see that all three of those different distributions could now be modeled using one variable and one distribution. And I'm not drawing this very well, but I meant to draw a bell curve here as well. But whatever the shape of the curve is, the linear transformation is going to transform each one of those individual x's from the three different exams to a uniform or a standard. I'm going to call it a standardized distribution. And these linear transformations have specific properties. Okay, and that's one of the things that makes it important, or makes this idea of linear transformation important. And it's because the mean for the new transform variable is equal to the original variable x after it's been put through the linear transformation. So what this first part says is that if I take the mean from x's distribution, or from, if I take the mean from the x data and multiply it by a and add b, that gives me the mean for the new variable, y. We could call that y bar. And then the standard deviation, now remember, this is another thing that gets confusing. So all right, so let me just make up a little example here real kind of quickly to show you what this is really saying, or the way I think you should think about what's going on here, okay? So if this is x's distribution, okay, and it's centered here at some number, say, oh, I don't know, let's just say 5, okay, and I transform, and suppose my linear transformation, I'll just make it really simple. It's y equal 2x plus 1, say, okay? Then what ends up happening is when I take, and again, I'm going to call this, and I'm drawing it like it's mu, but again, the book is using x bar, which is a little tricky here for how I'm trying to describe this, because really what I'm talking about is our population. So I'm just going to go ahead and stick with mu sub x. I'll be a little beyond this section, but I want to make a point here. So if I take this average from x's distribution and I put it through this transformation, okay, so I would take 2 times 5 plus 1, what I would end up with is 11, because 10 plus 1 is 11. And of course, the textbook here is saying that's y bar, but if we're talking about populations, we're talking about mu sub y, or the new populations mean. So if I draw this now on a horizontal axis, I label y, that means 5 over here got transformed to 11. Now the key thing to see is that there was a horizontal shift that happened there, okay? There was more. There were 2 things. There's a scaling, that's the multiplication, is the scaling, and then there's a shift to the right because of the plus 1. And that makes sense because the mean here is going to get the mean is a measure of center, so it's going to be affected both by a scaling, multiplication, and also by addition. But when we're talking about the standard deviation, okay, so say that we were talking about a population where the standard deviation was, say, oh, I don't know, let's say it's 2, okay. That means I'd go 5, 7, 9. The scaling would look like this, and then 3 and 1, say. Well, the new scaling is going to look different, because the thing to understand here is that the standard deviation is a measure of spread. So it doesn't really matter where that distribution is centered, okay? The standard deviation is only going to be measured by that measure of spread. And my scaling's not all that good, but the drawings here, my drawings aren't all that great. But the idea here is to say that, okay, so the standard deviation is going to be affected only by the scaling factor 2. So if I call so my new standard deviation for the y variable is going to be 4. So the scaling here is going to go 11, 15, 19. Okay, so this curve is going to be flatter and more spread out because it's going to have a bigger standard deviation. But the point I'm really trying to make here is that what's really going on with the standard deviation is the additive part isn't going to have any effect on the standard deviation, because the standard deviation is measuring spread in this direction. It has no effect on where the distribution's centered. It has to do with how spread out the distribution is. And that's why when we're converting the standard deviation, we don't add b. We don't add the constant, okay? We only deal with the scaling part of it. Again, I know this is a little bit confusing, but hopefully this will become more clear as we continue through the next chapters and the next lectures. But this is just a basic um, uh, introduction to the concept of standardization and linear transformation.